Hi, everybody. Welcome back. This is lecture 9, and we're going to start talking about probability, which is going to take us into several lectures into the second half of this course. So let's talk about basic probability. Some key concepts. What is probability? It's the measure of the likelihood of an event occurring, which ranges from 0, which are impossible events, to 1, which are certain events. So here's a scale that goes from 0 all the way to 1, and probability has to lie within this range. 0 being the impossible or never occurring events, and 1 being the most certain events. So right in the center, we have even chance, and we call that like a 50-50. So what we have on the left-hand side are events that are more unlikely, and on the right-hand side, we have events that are more likely, and right in the center, we have events that are equally likely and unlikely. So if we look at the probability of a patient needing a second treatment, and we're told that the probability is 0.2, that translates to 20%, and that's a 20% chance that they will need that second treatment. And that lies on this side of the 50-50 line, okay, 20%. So if we think about the numbers going from low to high, from 0 all the way to 1, 0.2 occurs on the left side of that. We have notation for probability. It's a capital P. And when we put parentheses E after that, we are referring to the probability of an event called E happening. And E could be any event. So we can replace the letter E there with any event, and P parentheses that event would be a numerical measure of the event happening, the probability of it happening. So if E represents some event, any event, we can calculate probability with this simple division. We take the number of ways the event can occur, and then we divide by the total number of possible outcomes. So I'm going to look at a very basic example. So P parentheses event E, or just P parentheses E, is notation for the probability of event E happening. So let's look at a basic example. In a clinic, 15 out of 50 patients have diabetes. Okay, what is the probability that a randomly selected patient has diabetes? So if you have 50 patients in total and 15 have diabetes, if you close your eyes and randomly select one of those 50 patients, the probability that one of those 50 patients will have diabetes is this ratio up here, the number of ways E can occur over the total number of possible outcomes. Well, the total number of possible outcomes in this case is the total number of people, and that's 50. And the number of ways that you can choose a randomly selected person with diabetes is 15, because there are 15 people with diabetes. So the probability is 15 divided by 50. Now, usually we express our probability in terms of a decimal or a percent. So we would take that 15 divided by 50 and convert it to 0.30, and turning it into a percent, 30%. So here, the notation that we're using, again with the capital E, and in parentheses, diabetic, meaning that we're looking for the probability of choosing a diabetic patient. Okay, so the interpretation of this, there is a 30% chance of selecting a diabetic patient at random from this group. The total number of ways the event can occur divided by the total number of possible outcomes. Let's try another one. If 8 out of 20 patients in a sample are smokers, what is the probability that a randomly chosen patient is a smoker? So we have a sample, and the size of our sample is 20. We're told we have 20 patients. 8 of those 20 patients are smokers. The probability of randomly choosing a smoker is going to be 8 divided by 20. Okay, so we're using the notation here again, P parentheses smoker. The event of choosing a smoker from the group is the number of smokers in the group divided by the total number of people in the group, 8 divided by 20. And turning that into a percent or first a decimal, 8 divided by 20 will give us 0.40, and multiplying that answer by 100 gives us 40%. To interpret this, it says that there is a 40% chance of selecting a smoker at random from this sample. Okay, the number of people in the sample is the denominator, and the number of people in the sample that are smokers is the numerator. Complementary events, in the notation that we use, is E with a little, looks like an apostrophe, but we say prime in math, E prime. It's the probability that event E doesn't happen. Probability of event E not happening, the probability of E prime is, we take 1 and we subtract the probability of event E. So for example, let's suppose we know that the probability that a patient has high blood pressure is 0.4 or 40%. The probability that the patient does not, that a group of patients, let's put this in context. What's the probability that a randomly selected patient does not have high blood pressure? Well, we take what we know that it's a 40% chance that they have high blood pressure. So the chance that they do not is 1 minus that 40%, 1 minus 0.4. That becomes 60%. So the probability of not high blood pressure is 1 minus the probability of having high blood pressure. That's 1 minus 0.40, and that is 0.60 or 60%. Complementary events, you're subtracting from 100 if you're dealing with percents, or subtract from the number 1 if you're working with decimals. So in this case, there is a 60% chance of selecting a patient without high blood pressure from the group. More complementary events. If the probability that a medication is effective is 0.75, what's the probability that it's not effective? Okay, the probability of something not being effective in this case is the complementary event of it being effective. So if we know that it being effective is 75%, the probability of it not being effective is 100 minus 75%, or 1 minus 0.75. So we take 1 minus 0.75, we can get 0.25, which is 25%. There's a 25% chance of the medication being ineffective for a patient. Okay, so real life decisions, let's put the importance of probability in an important context. Imagine a doctor estimates that there's a 25% chance a treatment will lead to complications. How would this probability affect a patient's decision about whether to undergo the treatment? Would you choose the treatment? What questions would you ask? What other factors would you consider? Realize that probability plays a role in decision making, especially in allied health, where risk assessment is essential. So the topic of probability, which we are just introducing in this lecture, really plays a very important part in all of statistics. So let's start talking about random variables. A random variable is a variable that we represent with the letter capital X. The value of the variable depends on the outcome of a random event. Let's look at an example. We have a sample of COVID-19 patients. They were all asked what symptoms they have from a list of symptoms. So imagine we have a list of a few symptoms here: cough, fever, fatigue, difficulty breathing, sore throat. Now, some of the people in our sample have all those symptoms, and some people in the sample have none of those symptoms. The random event is whether the COVID positive patient exhibits each symptom. Each patient either shows symptoms or does not, and this outcome is uncertain or random prior to observing the patient. X is going to be our random variable, and it is the number of COVID-19 symptoms. Each patient in this group, X, is variable. So some people in this group have no symptoms, where X would be equal to 0 in that case. Some people in this group have all symptoms, in which case X would be equal to 5. So for each person, the value of X is variable. The value of X changes. It's called a random variable. Okay, so this is a little bit tricky to understand at first, but just bear with me. We're going to look at a few examples, and this is going to become more concrete after we do some problems. Okay, discrete random variables. So what we just talked about was an example of a discrete random variable. It takes on a countable number of distinct values, typically whole numbers like 0, 1, and 2, for example, and so forth. In this previous example with the COVID-19 symptoms, X, which was the number of COVID-19 symptoms, was a discrete random variable. And the reason why it was discrete is because the value of the variable X from patient to patient was a discrete quantity, a whole number. It was either going to be 0 for no symptoms, or 1, or 2, all the way up to a total of 5 symptoms. The value of the discrete random variable cannot be any value between 0 and 1, for example. Either the patient has 0 symptoms, or 1 symptom, or 2 symptoms, or all the way up to 5 symptoms. There is no 1.5 symptoms. That's why it's called a discrete random variable. 0, 1, 2, 3, 4, or 5. Okay, now there are other types of random variables. The continuous random variables also exist, and they can take on any value within a range. For example, patient weight. Patient weight could be 150.4 pounds or 150.5 pounds. A person's weight is not restricted to be restricted to be exactly 150 pounds or 151 pounds, etc. So discrete random variables are restricted to these whole number gaps, whole number jumps with gaps in between. Continuous random variables don't have that kind of restriction. What we're dealing with today is only about discrete random variables. Okay, we will be talking about continuous random variables in future lectures. More discrete random variables. Let's count the number of daily medications a patient takes. Let's associate this with a random event, whether the patient takes each prescribed medication in their treatment plan. The discrete random variable X represents the number of medications taken per day by a patient, assuming a maximum of, say, 6 medications. And the values of X. X can be anything from 0, not taking any medications at all, up to 6. So imagine the situation where you have a patient who takes six medications or is supposed to take six medications a day, but sometimes some things happen. Sometimes people forget, or illness may cause you to be sick and you can't take all your medication. So the number can vary from day to day. The person can take all six, but there's a possibility the person doesn't take any, or just one, or two, or three, or four, or five. So that is our discrete random variable X. That is the number of medications being taken per day by a patient. So it is discrete because you can't take 1.5 medications per day. You take one or two, right? So there's that gap in between one and two. Let's look at another example. The number of physical therapy exercises completed by a patient in a session. So a person is prescribed a set of exercises to complete at a physical therapy session. But there are factors that could influence if all those exercises get completed. Maybe the person has to leave a little early that day, or there's just some restriction that they can't do an exercise or two. So let's look at our random event. The random event is whether the patient completes each exercise in a prescribed physical therapy routine. The random variable X, the discrete random variable X, is the total number of exercises completed out of a set of, say, 8 exercises. So the person has been prescribed 8 exercises, but they may not complete all 8. They can complete anything between 0 and 8 exercises. So that is the range of X. From 0, didn't complete any, all the way to 8, completed all the exercises. Couple more examples. The number of risk factors present in a patient's health assessment. The random event is whether a patient has each identified risk factor for a particular condition. So here there's 3 risk factors here: high blood pressure, smoking, diabetes. The person could have all 3 risk factors or none of those risk factors. So X represents the count of risk factors for a single patient. And X can range, well, if there were 4 key risk factors in total, X could be anything from 0 to 4. In this example, I have 3 risk factors, so X could be anything from 0 to 3 with just those 3. But we can have 4 risk factors, in which case X would range from 0 to 4. Number of preventative health screenings completed by a patient in a year. So preventative health screenings are those things that are used for preventing sickness, things like mammograms, cholesterol screenings, blood pressure, colonoscopy, things like that. So these are our preventative health screenings, and a patient may be told that they should get all of these in a year, but maybe they don't do all of them. So the discrete random variable X is a count of how many screenings they did complete out of the possible 4 that I have listed here. 1, 2, 3, 4. So they could complete none of them, or they could complete all of them. And so X ranges from 0 to 4. So now let's look at probability and these discrete random variables. Remember, probability is the measure of the likelihood of an event happening that goes between 0 and 1. If 1 of 20 COVID positive patients were randomly selected, would the probability of having all 5 symptoms, cough, fever, fatigue, difficulty breathing, and sore throat, would that be closer to 0 or 1? So imagine if you have a sample of 20 COVID positive patients and you randomly select a person from this group of 20. Do you think it would be very likely to have all 5 symptoms or not so likely? So would we be closer to here or closer to here? Most likely we would be closer to the side over here. Less likely. It's less likely for a person to have every single symptom. What about 2 or 3 symptoms? How likely would that be? Would that be closer to 0 or 1? Well, I think that would be closer to 1. The probability that a person has between 2 and 3 symptoms, I think that sounds more likely, and we can probably think that that's somewhere over here near 1. Now, those were our gut feelings, given what we know about COVID, but we can figure these out exactly. If we have sample data collected from patients, we can figure out using a discrete probability distribution, we could figure out what these 2 probabilities would be exactly and answer the question. So I'm going to show you how to build a discrete probability distribution from sample data and use that distribution to answer these questions. Now we are going to be building it's called a probability distribution table next. So our random variable X represents the number of COVID-19 symptoms in a patient. We have 20 COVID positive patients, and these are the reported symptom counts. 2 patients reported no symptoms. When there are no symptoms, the value of X, the discrete random variable X, takes on the value 0 for no symptoms. 2 patients fall in that category. 4 patients have 1 symptom. That means that X is 1. We have 4 patients in that category. 5 patients reported 2 symptoms. That's when X is 2. 3 patients reported 3 symptoms. That's when X is 3. 4 patients reported 4 symptoms when X is 4. 2 patients reported 5 symptoms when X is 5. Okay, so we are up to a total of 5 symptoms. So we are restricted in this example between 0 and 5 symptoms. A discrete probability distribution, and it's going to be in the form of a table. It will list all the values of the discrete random variable along with their probabilities. So given what we have here, these are all the values of the discrete random variable. All the values of X. And it ranges from 0 to 5. So our table that we're going to be producing next is going to range from X equals 0 to X equals 5. Okay. We are also going to associate each value of X with its probability, the probability of it happening, and all those probabilities are going to sum up to 1. So the probability distribution table. The first thing we're going to do is count our sample size, because if we're not provided with the number of items in the sample, we may have to figure it out ourselves. This time we were given 20. If we were not given 20, we would have to add up all the individual frequencies for the total. So we were provided with 20, but if we didn't have it, we would need to add up the 2 people when X was 0, the 4 people when X was 1, and so forth, add up each frequency, and this would sum up to our total. So that's necessary before we can calculate any probabilities. We need to know the total. So this is our total, and we're going to use that to calculate the probabilities that come next. So this is what a probability distribution table looks like, and we are going to complete the second column in a minute. I just want to explain the first column though. The first column represents all the possible values of X, starting with the lowest value of X and going up to the highest possible value of X. So it sounds like the name of it sounds like a frequency distribution table, but it's actually a lot simpler to build than the frequency distribution table. So the number of symptoms, the values of X go from 0 up to the max, in this case 5, And the P of X column is the probability of having 0 symptoms, the probability of having 1 symptom, the probability of having 2 symptoms, etc. And we're going to calculate that with just some simple division. So the table has 2 columns, X and P of X. That's the number of symptoms and the probability that a patient has that number of symptoms. So we list every value of X, 0 through 5, first, and then we calculate P of X using the sample data that was provided earlier. So we were told that there were 2 people in the total of 20. 2 out of 20 had no symptoms at all. 2 out of 20 had no symptoms. So we take that 2 out of 20 and turn it into a percent. 2 divided by 20, and we could do this on our calculator, I'll show you. 2 divided by 20 is 0.10. 0.10 times 100 is 10%. And we put that 10% in our P of X column right here. So 0.01, which is the same thing as 10%. Usually we either choose one or the other. We don't offer both in decimal form or percent form. We'll pick one or the other. In this case, I'm just showing you how to build this, so I'm providing both possibilities. So if you need some assistance building this, calculating these probabilities, let me take you to the calculator and show you that. So we take the number of patients with zero symptoms divided by the total number of people in the sample. This is 0.1, and multiply by 100 to turn that into 10%. Okay, and then we do that for all of the patients. I just am going to refer back to the slide with all the numbers. Okay, the next number of patients we had 1 symptom, and we were told that 4 patients in the sample had 1 symptom. So we turn that into a percentage. Okay, 4 patients in the sample had 1 symptom. That's 20%, 0.2 or 20%. 5 patients in the sample had 2 symptoms. That's 0.25 or 25%. And we continue that with all the data that was provided to us. We were given data for all values of X from X equals 0 to X equals 5. So we put that point, oh, I'm sorry, it's not 0.01, it's 0.1. 0.1, we put that 0.1, which equals 10% right here in the first row of the second column. That's because 2 patients showed 0 symptoms. Now, for 4 patients showing 1 symptom, we do 4 divided by 20, which is 0.2, 20%. We put that in the next row. 5 patients show 2 symptoms. 5 divided by 20 is 0.25 or 25%. And we keep going. 3 patients showed 3 symptoms. 3 divided by 20 is 0.15 or 15%. 4 patients showed 4 symptoms. 4 divided by 20 is 0.20 or 20%. And last, 2 patients showed 5 symptoms. 2 divided by 20, 0.10 or 10%. Okay, so I'm sorry, I messed up on that first one up there. That top one is supposed to be 0.10 also. To confirm that we calculated these probabilities correctly, let's add up all of the percentages and confirm that they all equal 100. That's one of the criteria that we have in probability distribution tables. They must all equal 100. So if we take 10 plus 20, that's 30, plus 25 is 55, and 16 is going to give us 70, and 20 is 90, and 10 is 100%. So that was done correctly. If any probability requires rounding, round the proportion to 4 decimal places. So like instead of 20, if our sample was 21, when we calculate 2 divided by 21, we would not have had an easy just 0.10 answer. Our answer would be 0.0952 when rounded to 4 decimal places. So we would convert that to a percent and it would be 9.52%. So sometimes that happens, and if you have to round, take it out to 4 places, and then when you multiply by 100, you'll have 2 places after the decimal point. Okay, so like I just said, we want to confirm that our probabilities add up to 1. So summing all those values up, either if we sum up the decimal versions, they'll equal 1. If we sum up the percentages, they'll equal 100%. So let's go back to some original questions that I presented to you, but use this table to answer them. So if 1 of 20 COVID patients were randomly selected from the 20, what's the probability of having all 5 symptoms? Now, we hypothesized that that would be a value closer to 0 than it was to 1, and it turns out we were right. The probability of having all 5 symptoms means x is equal to 5. The chance of that happening is the p of x value when x is 5. It's 0.1 or 10%. Let's answer the next question. If 1 of 20 COVID positive patients were randomly selected, what is the probability of having 2 or 3 symptoms? So to answer a question that involves multiple values of x, in this case 2, we have an x equal 2 and an x equal 3, we take those 2 values of x and we sum up the probabilities. So since the probabilities here are 0.25 and 0.15, we sum those up to make 0.4, 0.40, which is 40%. So the answer to that question was 40%. Now, I thought that maybe it was going to be closer to 1, and it turns out, nope, it's not closer to 1. It's pretty close to center. So it is 40%. Okay, so we use the probability distribution table to answer probability questions. Instead of just guessing what they would be like I did before, we look at the actual data, we construct probabilities, and we could answer probability questions using the table. So let's answer some more questions. What's the probability of a random patient having more than one symptom? So we use the table. Now the table, of course, building it in the first place, it has to be correct, but if we have a correct table, we can answer all these questions. What's the probability of having more than one symptom? Well, let me look at when x is more than 1. More than 1 means 2, 3, 4, and 5, according to this table, because we stop at 5. It doesn't go higher than 5. More than 1 is 2, 3, 4, and 5. So the probability of that happening is the sum of these 4 probabilities. So we would add up those 4 probabilities. I'm sorry, we're going to list all these questions here and then we'll come back and answer them. Okay. More than one symptom. So we are going to add up the 4 probabilities that correspond to x equal, I'm sorry, I did that wrong. Don't include 1 there. More than 1 means 2, 3, 4, and 5. So we're not going to include 1. We're adding the probabilities 25, 15, 20, and 10. And adding those up, our probability of that event happening is 70%. At least 4 symptoms. Okay, so the word at least is different than more than. Because when we say more than 1, we're not including 1, but when we say at least 4, we are including 4. So at least 4 involves both 4 and 5. So we would be adding up the 2 probabilities for 4 and 5. And that is 0.20 plus 0.10, which is 30%. What's the probability a random patient has less than 3, okay, less than 3 does not include the number 3. Less than 3, let me erase what's here on the board. Let's get rid of these. Don't want to make this more confusing. It's already a little bit of a tough topic, so I'm trying to keep it as basic as possible. Less than 3 does not include 3. Numbers that are less than 3 are 2, 1, and 0. So to answer the question, what's the probability that a random patient has less than 3 symptoms? We are going to add up the probabilities for x equal 0, 1, and 2. So 10 and 20 and 25. 10 and 20 and 25 is 55%. And the very last one, at most 1. So sometimes we are given questions using these. Let me write back here. Sometimes we are given questions using more than, at least, less than, and at most, and we have to understand what they mean. Okay, so at most in this case does include the number 1. At most 1 refers to both 0 and 1, and the probability of that happening is the sum of those two values of the sum of those two p of x's for x equals 0 and x equal 1. So we add up 10 and 20 and we get 30 there. So answering the questions based on a probability distribution table shouldn't be too difficult. Building the probability distribution table just involves using your raw data and taking each value and dividing it by 20. So let me go back to recall how we did that. Do you remember we had 4 patients showed 1 symptom, so we took 4 divided by 20, and that's what we put here. 5 patients showed 2 symptoms, 5 divided by 20, and we put that here. Okay. Okay, once that probability distribution table is created, you can answer questions off of it just like that. So we're going to now, for the next part of the lecture, we're going to discuss something called the binomial distribution. And we are going to be using our calculator for a part of this. The binomial distribution is a specific type of discrete probability distribution. It gives us a way to calculate the probability of a certain number of successes in a group of repeated trials. So we're looking for successes and we're looking at the a number of trials. Imagine you're performing the same action multiple times, like flipping a coin or giving a treatment or running a medical test. That is considered a trial. The binomial distribution helps us find the chance of getting a certain number of successful results in those trials. Here's a specific example. A treatment has a 65% chance of success. If 7 patients are given the treatment, what's the probability that it is successful in all 7 patients? The binomial distribution can help us answer this question. Not all probability questions can be solved with the binomial distribution, however. So to check that a problem meets the criteria, we can go through 4 criteria, and if it meets all 4, then the binomial distribution can be used to solve the problem. And we do this with the BINS acronym, B-I-N-S. First, B. B stands for binary outcome. Each trial or action has only 2 possible results, called the success and failure. So we have to ensure that when we're doing a problem, there are only 2 possible outcomes, success and failure. So for example, a patient either improves after treatment, which is considered success, or doesn't improve, which is considered failure. So all binomial problems can be divided into this success and failure categorization. a COVID-19 test comes back positive, success, or negative failure, or considering what you want to happen, if you want to not have COVID, then the negative would be considered the success. But either way, we can divide our results into two categories, success and failure. The I in BINS. The I in BINS stands for independent trials, and this means that the results of a trial don't affect one another. The outcome of one patient's treatment does not change the probability of improvement for the next patient. So in a properly conducted randomized experiment, trials are separated and one patient's experience does not have an effect on another patient's experience. So those are independent trials. And if done correctly, that's usually something that is satisfied in all medical trials. The N stands for the number of trials, and we're looking for the number of trials to be a fixed number. It's number of trials. We have a set number of trials that doesn't change. For instance, if we're testing 10 patients, that would be the number of trials. We stick with those 10 patients for this analysis. We don't add more or remove any partway through. So we have a number of trials, in this case 10, that is fixed and will not change. And the last piece, S, is for the same probability of success on each trial. The probability that any one patient improves is the same for all patients. If 65% of patients respond to a treatment, then each patient has the same 65% chance. So it means that there's no better chance for one patient versus another. Everybody has the same equal 65% chance. So here's an example, and we're going to go through BINS to see if we could use the binomial distribution. And if we can, we're going to answer this question and some others. Suppose we're testing, I need to correct something here. I'm going to fix this. Not 10 patients, 6 patients. Suppose we're testing a new treatment that has a 70% chance of improving symptoms in patients with a particular condition. We try this treatment on 6 patients. What's the probability that exactly 4 of these 6 patients will improve? Can we use the binomial distribution to answer this question? B-I-N-S. B, binary. Can we categorize our outcomes? Yes, we can, because either a person improves or doesn't improve, okay? Because the question is just asking what's the probability that 4 of 6 will improve. There's a 70% chance of improving. So we can, but there is a binary outcome, either improve or not improve. I, independent. Each patient's response is independent. We're treating each patient independently, so one patient's success does not influence another patient's success or failure. So I is satisfied. N, do we have a fixed number of trials? Yes, we have 6 patients. And S, the probability of success, which is considered improvement. Is that the same for every patient? Yes, it is. For every patient, it's 0.7 or 70%. Okay, so we have B, binary, I, independent, N, number of fixed trials, and S, the success is the same for every patient. Therefore, we can use the binomial distribution in this case. So let's do that. Let's look at our problem again. We have a new treatment that is 70% effective at improving symptoms with a particular condition. We have 6 patients we're testing this on. Okay, we're going to answer 3 questions. We're going to answer the first one that was posed before. Exactly 4 of these 6 patients will improve. We're going to do another part to the question. at least 5 patients improve, and another part, fewer than 3 patients improve. So let's remember the important details we're taking out of the word problem here. 70% chance of improvement, 6 patients, and each part has a different criteria. So the probability distribution table that we're going to be building to answer these questions are going to be based on some calculator output that we're going to get. And the reason why is because we're not working with raw data here. We're not working with the same kind of raw data that we were in. Let me bring it back. Where is it? This question. We were provided with raw values, how many patients had a particular number of symptoms. This question, this binary distribution question is different. Okay, we don't have that. We only have a percent of improvement, and we're going to use that to build the frequency, to build the probability distribution table using something called the binomial probability formula. So the first thing we're going to do is identify all the values of X. X represents the number of patients who improve. And so in our set of 6 patients, X represents the number of patients who improve. There could be no patients who improve, but there could be all of them, up to 6 patients who improve. So the values of X are every value between 0 and 6. In building the probability distribution table, that set of values of X becomes the very first column. And so we're going to make a row for each value of X. 0, 1, 2, 3, 4, 5, and 6. The next column, we are going to use our calculator and calculate a binomial probability. And for each one that we're calculating for, there's going to be 3 numbers that we're going to use in our calculations. We're going to be using 70%. That's considered the probability of success. And we're going to express that as a decimal. We're going to express it as 0.7 or 0.70 when we go to our calculator. The other thing that we're going to be using in our formula is the number of total trials. This is 6. We have 6 patients. We're going to be using that in the formula as well. And then the next value that we're going to be using in the formula, the third value is the number of X, the value of X. So the first time we do the formula, we're going to let X equal 0. The next time we use the formula, we're going to let X equal 1 and so forth. And we're going to go down the list. We're going to run this formula, the binomial probability formula, 7 times for every value of X on this list. And we're going to use our calculator. Okay, so how do we calculate a binomial probability? We're going to use binompdf, this function on our calculator. If we press second and then distribution, we'll scroll down and find it with letter A. I'm going to go jump to the calculator so I could do this with you. So just give me a moment. Okay, so here's my calculator. Second distribution. Do you see above the vars key, there's a small, in blue, you see DISTR. That's the distribution area. So we're going to hit second and that vars key, which brings up the distribution. Sorry, that didn't work. Let me quit this. Second, vars. I'm sorry, it was fine. I just wasn't seeing it. We have to scroll down. Okay, binomial PDF is not immediately visible, so let's scroll down to A. Okay, so you have to scroll down a bit. There's 2 that look very similar. The first one is in A and the next one is in B. Binom PDF is different from binom CDF. So stick with binom PDF for the work that we're going to do today. You're going to hit enter on binompdf, and the number of trials is going to stay the same for this whole problem. Like I said, we were going to do binompdf. We're going to do this 7 times, but the number of trials is staying the same. Every time we do this, we're going to be referring to the 6 patients that we're testing this treatment out on, or whatever it was. Yeah, we've got a treatment for patients with a particular condition, and there's 6. This is never changing. P represents the probability of success using that treatment. Now, that never changes either. From patient to patient, the probability of success was given to us as 70%. So we're going to put in here, we're going to use it as a decimal. We're going to write 0.70 or zero point 0.7. That's never going to change for all 7 of these binom formulas we're going to apply. But what will change between each of the 7 is the x value. The x value is exactly what you think it's going to be. It's the value of x that corresponds to each row of the table. The first row of the table, x is 0. The next row of the table, x is 1, and so forth, and it goes all the way down to x equals 6. We're going to do this 7 times, where x value is going to change each time between 0 and 6. So let's paste this and then hit enter. Then hit enter again. Okay. This E-4 here means that our calculator is putting this in scientific notation. So this is not the easiest thing to explain while I'm looking at the calculator, so I'm going to have to bring you back to the slideshow for a second. So just give me a moment and I'll pause this. Okay, so we go to our calculator, we put in the number of trials, 6, we put in the probability of success, 0.70, it's always going to be that for this problem, and the x value is going to be the value of x in each row, and when we put in an x equals 0, when we put in an x equals 0 on the calculator, it was 7.29 E-4. So let me 7.29 E-4. Okay, 7.29 E-4. Now, if you've never seen this, it's a little intimidating, but it's not so bad. It means that our calculator is displaying this number in scientific notation, and it's equivalent to saying 7.29 times 10 to the -4th. So to get 7.29 times 10 to the -4 in a standard notation, we're going to move the decimal point. So we're going to take this decimal point between the 7 and the 2, and the -4 means you're going to move it 4 places to the left. 1, 2, 3, 4, and put a new decimal point in. Then fill in those empty spots that you just created with zeros. So what was 7.29 is now 0.0007. And that is the probability answer when x equals 0. So to refresh again, when you see 7.29 E-4, the -4 means move the decimal 4 places to the left. We may see this a few more times this semester, so when you see that come out on your calculator, you know what to do with it. Move your decimal place to the left when you see the negative value in scientific notation. If it was a positive value, you would move it to the right, but we don't see that this semester. We're always going to see it on the left side. So our probability, and this is super small, the probability that nobody in our sample are successful is 0.0007. And we put that in the table in the first row when x equals 0. And now when x equals 1, we just change on our calculator, we're going to go back to binompdf and we're going to plug in um, the trials 6. The probability of success on a single trial is 0.7 or 0.70, and this time change the X value to 1. And we calculate that probability. Now that's definitely going to be bigger than the first one. This one comes out to be 0.0102. So rounding to 4 decimal places for all of these, 0.0102, we see it gets a little larger. Okay, so this is the probability that one person is successful in our group of 6. The probability that one person is successful, and that's just a little over 1%. And we keep doing this for all of them. The probability that 2 people are successful, the probability that 3 people are successful, that 4 and 5 and all 6 are successful. So if you think about this, we start off with no patients being successful up here, and that's a really small probability. The probability that all the patients are successful down here, do you think that's going to be a really big probability or a really small probability that all 6 are successful? Well, let's calculate it and see what happens. Let's go to our calculator. So I'm going to go back to second distribution, letter A, binompdf. I've got 6 trials. I've got a probability of success of 0.70 and X value. Well, I did 0 and 1, and you would go through all of these. You would do 2, and then you would do 3 and 4 and 5 and 6 and fill in the entire table. I'm going to leave that to you if you'd like to do that. I just want to show you what happens with 6. This is the probability that all 6 patients are successful. And the chance of that happening is 0.1176. 0.1176. So I asked if you thought it was going to be a large probability or a small probability. Well, it's not large. It's not as small as none being successful, but it's not huge, right? So what happens in our table, and I'm going to flip back now to the slideshow. What we see in our table is that probabilities may start off very small, then they'll go up a little bit, and then they'll go down a little bit as we go down the table. And I'll show you what I mean. Okay, so here's our completed table. So it started off with a really, really small probability, and then it went up, and it got a little bit bigger. So this is about 1%, and this is a little more than 5, or close to 6%. And then it got bigger, 18%, and then it got bigger, 32%. That was the largest of all these probabilities, because then it went down again, 30%, and then it went down again, about 11.76%. So this is our completed probability distribution table using the binomial probability formula. And we can answer these questions now. First, let's confirm that our probabilities sum up to 1. Now, since we rounded all of these probabilities, it's possible that when we add them up, we're not going to get something that's exactly 1, but it should be close to 1. So if we add them all up, you're going to see that we do get something close to 1. So 0.9998, which is good enough, okay? If we were way off, then there would probably be an error there. But the only reason why this is not exactly 1 is because each of these probabilities is an approximation because we rounded each of them. And so in the end, when we sum them all up, we're not going to have exactly 1. Okay, it's an acceptable error. So now let's go back to the original questions and see if we can answer them using this completed table. This table now is our answer key. So the first question said, what is the probability that exactly 4 of 6 patients will improve? So of our value of x, our values of x, exactly 4 means when x equals 4. The probability of success, the probability that that all 4 patients improve is 0.3241. So that is the answer to part A, 0.3241, and turning it into a percent, 32.41%. Okay, I have all the answers out for the next part, so let's just take it step by step. At least 5 patients improve means that we're considering values of x for 5 and 6. At least 5 means both 5 and 6. So we take both probabilities when x equals 5 and x equals 6. We add them both up, and the answer becomes 0.4201 or 42.01%. And then the last question, fewer than 3. Fewer than 3 means 0, 1, and 2. So adding up those 3 probabilities, adding up the 3 probabilities that correspond to x of 0, 1, and 2 gives us 0.0007 plus 0.0102 plus 0.0595. It sums up to 0.0704 or 7.04%. Now on your homework, when you're asked questions like this, you will be told whether or not to answer in the form of a decimal or in the form of a percent. So just follow the instructions and answer as the question asks. Both of them are valid probability answers. Okay, we're going to try another question for the binomial probability, using the binomial distribution to answer binomial probability questions. A new vaccine has been shown to be 85% effective in preventing infection. In a group of 5 healthcare workers who have received the vaccine, what's the probability that infection is prevented in all 5 workers? Infection is prevented in more than 2 workers. Infection is prevented in at most 2 workers. Okay, so going through the criteria for the binomial probability, the BINS, the 4 criteria, the 4 criteria. Hold on a sec, let me go back here. We have a binary outcome. We either have infection being prevented or not. So we have a binary outcome. The trials are independent. Each healthcare worker's success does not influence the next healthcare worker's success or failure. BIN, the number of trials is fixed. We're dealing with 5 healthcare workers, and we're not changing that through the course of the program, through the course of the experiment. And the BINS, the success probability is 85%, and that is the same for every person in the set of trials. So BINS, we satisfy all these criteria, and therefore we can use the binomial distribution to answer this question. First, let's identify all the possible values of x. X represents the number of workers in whom infection is prevented, the number of workers in whom infection is prevented. And given the way the problem is phrased, you can read that in each of these parts. In all 5, in more than 2, and at most 2. So x is the number of workers. The possible values of x range from 0 to 5. You can have none of the workers have infection prevented, or all 5 can have infection prevented. So this would mean that everybody's successful, and here everybody is a failure in this case, when x is 0. Okay, so we're going to build the probability distribution table where the column of x goes from 0 to 5. So X represents the number of workers, and we're going to do 0, 1, 2, 3, 4, and 5. P of X, we're going to get this by using binomial probability on the calculator. So I will do the first couple with you, and then you can pause the video and fill in the rest of the values in the table. So in this example, we have 5 trials. So let's go to binompdf. And we have 5 trials. The probability that this vaccine prevents infection is 0.85. It's 85%. And X is going to range from 0 to 5. X equals 0 is the first one. And then we're going to do X equal 1 and X equal 2, etc. So when X equals 0, again, we have scientific notation. This -5 means we're moving the decimal place over 5 places to the left. 1, 2, 3, 4, 5. We're filling the holes with zeros, and it turns out when we round this, it will be 0.0001. 0.0001 when this is converted to standard form. Let's try binom distribution, binom PDF again with X equal 2. Sorry, X equal 1. And what do we have? Okay, this one, 0.0022. And let's do it again. The calculator does remember what you put in the last time, so you only have to change the X value when X is 2. And it's getting bigger, 0.0244. And you can do the rest. That was 0, 1, 2. And then you'll also calculate the same thing for 3, 4, and 5, X values of 3, 4, and 5, and you'll put those in the table. Okay. So now we can answer our questions. If our table is complete, using binompdf on the calculator, that's how we filled in this column, we can answer A, B, and C now. A, what's the probability that infection is prevented in all 5 workers? All 5 means when X is 5, and the probability of that being successful, all 5 being successful, is 0.4437. Now, the reason why is because it's an 85% effective vaccine. Okay, so that's why we see this so much bigger than in the previous example, where it was all 6, the probability came out to be about 11%. Here it's about 44%, 44.37%. Okay, more than 2. More than 2 means 3, 4, and 5. So we're going to add up the 3 probabilities that associate with X equal 3, 4, and 5. Okay, so X equal 3, X equal 4, and X equal 5. And that's big, 0.9734, 97.34%. And the last part, at most 2, means 0, 1, and 2. So we're adding up the 3 probabilities that associate with those values of X. And we get 0.0267 or 2.67%. Okay. So those are 2 helpful examples on using the binomial distribution to answer questions on the binomial probability. And you'll have some homework questions like that. Let's look at why this is useful. So a bigger picture of why we do this stuff in the first place. Using the binomial distribution helps us make predictions in healthcare. So for instance, if we know the success rate of a treatment, we can use it to estimate how many patients are likely to benefit from it in a group. Knowing probabilities helps doctors and health organizations make better decisions. such as deciding whether a treatment is effective enough to use more widely. Clinicians use probability results to assess risks and benefits. For instance, if a treatment has a high probability of achieving the desired outcome, it may be prioritized. A low probability, like 15% of vaccine or treatment effectiveness in a group of people, may require further study or alternative treatment strategies. A limitation of the binomial distribution is that it only applies when outcomes are binary. So remember, success and failure, that's the only case where you're allowed to use the binomial distribution. So it is not suitable for complex or continuous outcomes. That's coming in future lectures. So the binomial distribution, very, very useful if we have binary outcomes and a fixed number of trials. So let's look at the probability histogram we created. Or did we create this one? No, I'm sorry. This may be something that I just presented at the beginning. And let's just assume we have a completed probability distribution table. And from this completed probability distribution table, we are going to build a histogram. Remember that histograms are that visual graph where the bars have heights that represent frequencies. Well, in a probability histogram, we do have bars, but the heights of the bars represent probability. So it's a visual graph of a distribution table. The values of x are placed along the horizontal axis. Probability is the vertical axis. So the height of each bar is a representation of its probability. So horizontal axis would be the values of x. In this case, number of COVID symptoms. We have 0, 1, 2, 3, 4, and 5. Okay, each bar or each rectangle represents each of those different values of x. The height of each bar is the probability. So when x is 0, the height of this rectangle is the probability of no symptoms. X equals 1, the height of this rectangle is the probability of only one symptom, probability of 2 symptoms, etc. Okay, so on the on the vertical axis, what we have instead of a frequency, like we did with frequency distribution tables and histograms, instead of that, we have probability. So probability in this case, the max probability we have on this table is 0.25. So you can see that's the max probability I have on this histogram. So let's answer some questions by reading this histogram. Knowing that the height of each rectangle is the probability of the event happening, the height of the first rectangle is 0.10, then 0.20, then 0.25, 0.15, 0.20, and 0.10 again. The probability of a random patient having more than one symptom, more than one means 2, 3, 4, and 5. That would be the sum of these 4 rectangle probabilities. Adding those 4 rectangles up, we have 70%. The probability of a random patient that has at least 5 symptoms, well, we only have 5 here, so at least 5 just means 5 in this case. Oh, I'm sorry. I think I meant to say, let's see, what did I mean to say with, okay, looks like I have a bug in this question. I'm not sure what I intended here, so let's forget about that one for a moment. Let's do this next one. What is the probability that a random patient has less than 3? Okay, I hope I got this one right. Less than 3. So we have 0, 1, and 2. That would be 0.10 plus 0.20 plus 0.25, and that's 55%. And the probability a random patient has at most two. At most two means 0 or 1. I'm sorry. At most two means the same thing as less than 3. Okay. At most two is the same thing as less than 3. It's 0, 1, and 2. So okay. I think I mixed. I missed this one too. I think what I intended to say here has at most one symptom. At most one means 0 and 1. So that would be the sum of 0.10 and 0.20, and that's 30. And I think what I meant up here, let me fix this one. I think what I meant over here was at least 4. I think I meant at least 4. And if we think about at least 4, it means 4 and 5, and that's the sum of 0.20 and 0.10, and that's where the 30 came from. So I will fix the slideshows. So if you refer to this in Brightspace, you see the right numbers, but that was my intention here. Okay, so probability histograms are reflections of distribution tables, visual representations of distribution tables that you can use to answer questions as well. Probability histograms are going to become important in the following lectures when we start discussing continuous probability distributions. So this lecture is an intense lecture. I hope that you stuck with me. But it's very important because it is the basis for the probability work that we're going to be doing coming up soon. So try your best. Ask me if you have any questions, and I'll see you at the next lecture.